Welcome to the BKR chemistry classes. The second part of spectroscopy, I'm going to deal with the number of signals. How many signals will we get in proton and carbon NMR spectroscopy? So, generally, the number of signals depends upon the number of different types of protons. So, you can easily look into the environment of protons and you can tell the number of signals. So, you can see these two CH3 have same environment. They have same environment. So, they'll give you only one NMR signal. So, that corresponds both for proton and C13. Both proton and C13 will give you only one NMR signal. Now, coming to this problem, you have a chlorine, the adjacent carbon and CH2, the next CH3. So this will give me two proton and two carbon signal. So I have two different types of protons because the CH2 is directly attached to Cl and the CH3 is attached to CH2 followed by Cl. So they are having different environment. So if they have different environment, they'll give you different signals. If they have same environment, they'll give you same signal. So the number of NMR signals equals the number of different types of protons in a compound. And the protons in different environment give different NMR signals, and if the protons are equivalent, they'll give you same NMR signal. So for example, ethyl methyl ether, you can see this O is attached to CH2 and CH3. This CH3 and this CH3 are not same because this CH3 is attached to oxygen and this CH3 is attached to CH2. So I'll be having three proton NMR signal. For this, I'll be having A, B, C, A, B, C. So A, B, C. So three NMR signals for proton, and also I'll be having three NMR signals for carbon because this is CH3 carbon, this CH2 carbon, and this CH3 carbon. Now, whenever you have cycloalkanes and alkanes, try to write them in the structural formula or the geometrical form so that you get the right answer. For example, if I look at this problem, I will say that I have CH2, CH2, CH, and Cl, chlorocyclopropane. Now I'll say that these two CH2 have the same environment. They are attached to CH followed by Cl. Okay, so I'll say that I'll be having two carbon signal and two hydrogen signal. So these two will be same. These two will be same, and this carbon and H will be different. So two carbon. So these two carbon are A, and this carbon is B. Similarly, the proton. So I'll be saying two carbon, two hydrogen, but you'll get a wrong answer. So whenever you have a cycloalkane, try to write them in the structural form. Now you can see that in this you have hydrogen above the plane and hydrogen below the plane. So these hydrogen assist to the chlorine and these hydrogens are trans. They are trans to the chlorine. So these two hydrogen will be same. So they are, suppose as a proton, and these two hydrogen will be different. They'll be giving B proton because these two hydrogen assist to the chlorine and these hydrogens are trans to the chlorine. So they have different moments. So these hydrogens have cis hydrogen, they have hydrogen, but these have chlorine. So they are different. So the number of hydrogen will be A, B, and C. I'll be having three proton signal. Let us consider the alkene. So if I look into this molecule like this, I'll say that okay, this is A, this is B. So I have two proton signals and two carbon signals. I have two proton and two carbon signals. But again, you will end up with the wrong answer. The carbon will be right. So I have one carbon, two carbon. So I have two carbon signals. I have what about hydrogen? So they have hydrogen which is cis to the chlorine. So A hydrogen. I have a hydrogen which is trans to the chlorine, which is B hydrogen, and this hydrogen is geminal to the chlorine, so they are C hydrogen. So I'll be having three hydrogen signal and I'll be having two carbon signal. So whenever you have a cycloalkane or alkene, keep in mind that you write the structural formula. Okay. Next, let us do some simple problems. So I have this CH2, CH2, Cl, Cl. So this both are same because this CH2 is attached to chlorine, this CH2 is attached to chlorine. Now I'll let you know a very simple method by which you can easily find out the number of signals. So you can use plane of symmetry. You can use plane of symmetry. So you can use a symmetry element, plane of symmetry sigma. So a plane of symmetry is a symmetry plane which cuts the molecule into two equal halves. Two equal halves. So if I cut the molecule into two equal halves, whatever is lying on the plane will be identical or they'll be equivalent. So this CH2 and this CH2 are identical. So I'll be having one proton signal and I'll be having one carbon signal. So I'll be having one and one. Now I cannot cut the molecule like this because here I have chlorine, here I have bromine. So here in this case, I'll be having all the hydrogen will be different, all the carbon will be different because this particular carbon is attached to chlorine and this carbon is attached to bromine and this central carbon is attached to both CH2 on either side with Cl and Br. So I'll be carbon signal and three hydrogen signal. Consider this methyl acetate. You have this CH3 attached to oxygen, this CH3 attached to C double bond, or they're different. I cannot cut the molecule. So there is no sigma plane. There is no sigma plane. Therefore, again, I'll be having two hydrogen signal and I'll be having three carbon signal. Now you're into this particular molecule, ethanol. You have hydrogen of methyl, hydrogen of methylene, and you have OH hydrogen. So three hydrogen signal. And for carbon, I'll be having two carbon signal. So a very simple problem I have taught you is very simple method. So cut the molecule, I'm able to cut the molecule. So these two hydrogen are same. So I'll be having one hydrogen signal. Here I cannot cut the molecule, so I'll be having two hydrogen signal. Here, as we have told cis, this is trans, this is cis, this is trans, and this is geminal. So I'll be having three hydrogen signals. Talking about the plane of symmetry, now there's something known as enantiotopic and diastereotopic, or I can have topicity of ligands and groups, which you might have studied in stereochemistry, topicity of ligands and groups. So we have three category. We have something known as homotopic, enantiotopic, and diastereotopic. Homotopic, enantiotopic, and diastereotopic. Now, how to easily arrive at them? So, a simple method is exchange of ligands or substitution of ligands one by one. So, now I'll try to explain this concept very simple method. Okay, suppose I say take this particular molecule, hydrogen A, hydrogen B, and CH3. I'm questioning you. What about the topicity of this HA and HB? So, what you can do is you can exchange them with a ligand Cl, suppose. So I can replace them one by one with Cl. So if I replace Ha by Cl, if I replace Ha by Cl, I'll be having CH3, Cl, Hb, I'll be having CH3. And when I replace Hb by Cl, I'll be having CH3, HCl, and I'll be having CH3. Now you can see you have CH3, 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 CH3. They are identical molecule. You can rotate them and you can get the molecules. So they are easily exchanged. So they are identical. So they are known as homomers. So these two ligands are known as homotopic. So on exchange of the methylene hydrogens, if I get homomers, they are homotopic. Okay. Is that clear? Okay. Next. Suppose I take another molecule. I take HA, HB. I'm talking about the topicity of these ligands. Same as the previous method, substitution method. I replace them one by one. So I'm going to replace HA by Cl and HB by Cl. So when I do that, so I'll be having Cl, HB, CH2OH, and CHO, HCl, CH2OH. Now you can see their mirror image. They are non-superimposable mirror image, or what we have got as enantiomers. So on exchanging the ligands, if I get enantiomers, these two hydrogens becomes enantiotopic. So that is what is shown here. So I replace one by one the HA and HB by Z, they have replaced and they've got enantiomers. So if I get enantiomers, then it is enantiotopic. Now keep in mind that whether you have homotopic ligands, the CH2 ligands are homotopic or they are enantiotopic, then these hydrogens of CH2, they are equivalent. They are chemically equivalent and they'll give you same signal. They'll give you one signal. So these two hydrogen will give you only one signal. So when substitution of two hydrogen by Z forms enantiomers, the two hydrogens are said to be equivalent. They give you a single NMR signal, and these two hydrogens are called enantiotopic protons. They are enantiotopic protons. Now coming to the next one, diastereotopic. So if I replace the ligands HA and HB, so this CH2, they are topicity of ligands, I'm going to see. When I replace them, if I get diastereomers, on the substitution of ligands, then they are known as diastereotopic hydrogens. And these diastereotopic hydrogens are not equivalent. They'll give you two NMR signals. If I get homomers, the methylene protons are homotopic. If I get enantiomers, the methylene protons are enantiotopic. If I get diastereomers, enantiomers are mirror images of each other, non-superimposable mirror images of each other. Diastereomers do not have this mirror image concept. So these diastereomeric protons, they'll become diastereotopic. Now keep in mind, homotopic and anisotropic are chemically equivalent. Diastereotopic protons are chemically non-equivalent. So if they are chemically equivalent, they'll give you same signal, only one signal. If they're diastereotopic, they're chemically non-equivalent, they'll give you different signals. Okay. So very simple. So what I can do in order to find this homomers, enantiomers, diastereomers, or homotopicity, enantiotopicity, and diastereotopicity, what you do is if the protons are exchangeable C-n axis, C2, C3, C4, whatever, if they're exchangeable by axis of symmetry, then they are homotopic. If they are exchangeable by mirror plane, they are enantiotopic. If I have no symmetry elements, then they are diastereotopic. So if you are able to cut the molecule or if you're able to rotate the molecule, they become chemically equivalent and they'll give you one signal. So hydrogens which are overlapping by sigma plane or they are exchanged by the axis of symmetry, they'll give you similar signal or one signal. They are chemically equivalent. Keep this in mind. It becomes carbon signals are very similar to that of the proton. Here I'll get only one signal because they have same environment. Here I'll get two signals. Here I'll get three signals. So that's what we have seen already. Okay. So now what did we see? If it is homotopic, they are exchanged by axis of symmetry. They are chemically equivalent. If they are anisotropic, they are exchanged by plane of symmetry. They are chemically equivalent. So here what we will get? We'll get only one signal for such protons. If they are diastereotopic, there are no symmetry elements, they are chemically non-equivalent, they'll give different signals. That is how you will try to find out the number of signals. I've given you a very simple method also, axis of symmetry, plane of symmetry, no symmetry. I'll give you another clue, very simple clue. Just check for a chiral carbon in a molecule. If you have a single chiral carbon in the molecule become diastereotopic. So any geminal CH2 hydrogens, the hydrogen attached to the same carbon or any geminal dimethyl attached to the same carbon, they'll become diastereotopic. Keep this in mind because it is a very important concept. So they become diastereotopic. They'll give you different signals. They'll give you different signal. Keep this in mind. If you have a chiral carbon in the molecule, the hydrogens or the geminal methyl becomes chemically non-equivalent. They become diastereotopic, so they'll give you different signals. The 19th question. So I can rotate this molecule very easily. So on rotation, this CH3 will be same. So A proton. This CH and this CH will be same. Therefore B proton and this hydrogen here and the hydrogen here, they'll be C hydrogens. This carbon does not have an hydrogen, so I'll be having a CH2 here. That will be D. So totally I'll be having four signals. Next one. They have asked for carbon. Just always look into the problem whether it is hydrogen or carbon. So I can cut the molecule like this. Here I can cut the molecule. So when I cut this carbon and this carbon is same, so I put them as A. This carbon and this carbon is same, so I put them as B. Now this particular carbon and this carbon, they are different because this carbon is attached to C double bond or this carbon is attached to CH2. Okay, so this is different. So this will become C, this will become D. Now this carbon will become E and this carbon will become F. Why? Because this carbon is attached to C double bond O. This carbon is attached to CH, which is attached to CH2. So E and F are different. So I'll be having A, B, 1, 2, 3, 4, 5, 6. So answer is option 3. Now look into this molecule. I can rotate this molecule. I can cut this molecule like this. Okay. So what happens is that every single atom here, so this carbon, this carbon, this carbon, this carbon, you can see they are attached to the bridging carbon CH2. So they are as identical. They have a neighboring Br, carbon Br. See, exactly same. In this side you have a CH. So this carbon A, all the carbon. Now this bridging carbon, there'll be B, B. I can cut them with plane of symmetry. I can rotate them. So I have the symmetry elements which will make them exchangeable. Now this carbon containing the Br, they are C. So all the carbon containing Br are C. Okay. And now this carbon which contains the hydrogen, okay, CH. So this becomes D. So I have here one, I have here one, I have here one, I have here one. So totally I have A, B, C, D. A, B, C, D. So I have four signals. So answer is four. Okay. Now the proton NMR spectrum of methanol, the two methyl groups are expected to display signals. So since this molecule, so a very tricky problem. So you will think that they are same, but since I have a chiral carbon, what did I mention already? If you have a chiral carbon, all the geminal group will become chemically non-equivalent. They'll give you two signals. They'll give you two signals. Option 3 is wrong. Option 4 is wrong because it's showing that 6 hydrogens are equivalent. So that is wrong. Because both the CH3 are chemically non-equivalent. They are attached to a carbon which is chiral in nature. So whenever I have a chiral carbon, there'll be no symmetry element. No symmetry element. So they become chemically non-equivalent. So now it could be either one or two. Since both are alkyl, they'll be having this particular range. Two. I'll come to this bit later. The next video I'll just talk about the value, that is chemical shift values, delta values in ppm. So there I'll discuss this problem again to show you the values of the two methyl groups. So for now you can just keep in mind that you will not have same signal for all the six hydrogen. They'll be having different signals. Next problem, they are asking for R4 methyl pentane 2 all. So this is a molecule. You can see you have a chiral carbon here. You have a chiral carbon here. So now, whenever I have a chiral carbon, this geminal methyl will be no longer equivalent. They'll become chemically non-equivalent. So they'll ask for carbon. So I have one carbon, second carbon, third carbon, fourth carbon, fifth carbon, sixth carbon. So if you have not known this enantiotopic diastereotopic concept, you will land into wrong answer. You will say 1, 2, 3, 4, and these two you'll put as 5. So you'll get wrong answer. But since now you know that diastereotopic protons are chemically non-equivalent, they'll give you two different signals. Now we come to know that we have totally 6 signals. So answer is 6. The broadband decoupled. So this coupling, decoupling, the number of splitting, the splitting pattern, that I'll teach in the next video. For now, you just try to find out the number of signals. Okay. So number of different carbon. How to find out? So okay. So I have two plane of symmetry. Now all the four quadrants, 1, 2, 3, 4, they are chemically equivalent. Check this carbon attached to OH. This carbon attached to OH. Both the side you have CH. So now count the number of carbon only any one of the quadrants. So let me take one quadrant one. 1, 2, 3, 4, 5. So I have 5 carbon in this particular quadrant. Okay. So I'll be having 5. So option 1 is gone, option 2 is gone. It becomes very easy if you find one clue, you are able to strike out two answers. It becomes 50-50 chances we always get in almost all the problems of CSR and gate. Okay. Now cut this molecule like this. So when I cut the molecule like this, I cannot cut it further because I don't have symmetrical positioning of the OH. So now any half of the molecule, I count the number of carbon. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Don't forget to count these bridging carbons. Okay. Usually students forget this and they lose the mark. So I have 10. So see, they are giving you a point of confusion. So they know how the students answer. So they're giving the answer as 8. So you will say 1, 2, 3, 4, 5, 6, 7, 8. Finished. So you'll say 8 and you will get the wrong answer. but the answer is 10. So the option is option 3, not 4. Whenever I have a chiral carbon, the methylene protons will become chemically, what? Tell me, finish it. Chemically non-equivalent. They'll give you different signals. So I have methylene hydrogens here, I have methylene hydrogens here. This is CH hydrogen and this is CH3. So now these will become chemically non-equivalent. Do you remember talking about diastereotopic protons? So they'll become diastereotopic because you'll get diastereomers. They are not mirror images. There'll be no mirror plane. Whenever you have a chiral center, you'll have no mirror plane. Okay. So I'll be having one, two, three, four, five, six, seven, eight. This CH3 9. This CH3 10. So I'll be having totally 10 proton signals. See, very interesting questions. This particular problem asked in December 2013 asked for two singlets in proton NMR. Since we have not yet gone into the spin-spin coupling and spin-spin splitting, so this topic I have not yet discussed. So I will stick on to the two signals. So two signals in proton NMR and three signals in carbon NMR. Okay, so look into the four molecules. Now, as I've mentioned, you just try to cut the molecule. So first molecule I'll cut like this. So I can even cut like this. So when I cut like this, what happens? This CH3, all the four CH3 are chemically equivalent, so they'll give you one signal. So they all will be one signal. And these hydrogens, they'll be also chemically equivalent, they'll give the second signal. So this particular molecule gives hydrogen, proton NMR gives two signal. But carbon, let's see. So you have a carbon here, CH carbon, CH carbon. This are CH3, 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 and you have a carbon here. Okay, don't forget the benzene carbon. Now cut the molecule. So I cut the molecule like this, I cut the molecule like this. So what happens? All these carbons are same. So they'll give a signal. All these carbons, which are the benzene carbons, they are again they are same, they are quaternary carbon, and this CH carbons will become C. So here, this particular molecule gives two signals in proton NMR and three signals in carbon NMR. So they've asked for two signals in proton and three signals in carbon. So answer should be option A. But let us check the other options. What is the answer? Now, second molecule, just cut the molecule. I can cut the molecule like this. This is where I can cut it. I cannot cut it the in a perpendicular fashion because I have methyl here, but I don't have methyl in this particular carbon. I don't have methyl here. So now when I consider the hydrogen, so I have an hydrogen here. I have an hydrogen here. CH3 hydrogen, CH3 hydrogens. Here also I have a CH3 hydrogen, and I have an CH3 hydrogen here. So now you can see that this CH3 is having two CH3 in the ortho position, but this CH3 does not have that. So this will give you A signal, B signal. And these two are following a pattern whereby they lie on the mirror plane, therefore they'll be giving the same signal. So C carbon, C carbon. Now the carbon here, they'll be having D carbon. And the carbon here will be having E carbon. And this carbon will be F and G. So I have lot of carbon signals. So this is not the right answer. Now coming to this, I have CH3, 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 CH3. So this is carbon A signal, B signal. I have C, D, I have E. So lot many signals. This is also not the answer. Now let us check this one. So I can cut this molecule like this. So this is CH3, CH2. Already I have two carbon signals. Then I have benzene signals. So oh my god. So I can cut this molecule also like this. But anyways, I have one, two. I have three here, three carbons, but there are three, and also I have four here. So this is not the right answer. So obviously the right answer is option A. Suppose I ask you, find out the number of hydrogen signal in each case, number of proton and NMR signals. What will be your answer? Okay, so let's check. So here I'll be having this CH3, this CH3, and this CH3. I have a CH3 here, and I have an hydrogen here. So I'll be having hydrogen A. This will be also A because I have a plane of symmetry here. I have a hydrogen A, hydrogen A. I have a plane of symmetry in the center, and this will become B, C, and this will be D. So I have four signals in hydrogen, proton, and NMR. Let us check this. I can cut this molecule like this. I can cut this molecule like this. So I have CH3 here, CH3 here. I have an hydrogen here, hydrogen here. They all fall in the plane of symmetry. Therefore, I have one, two, three. So I have three hydrogen signal. I have three hydrogen signal. Okay. Now let us consider this. I can cut the molecule like this. I can cut the molecule like this. Now look into this molecule. I can cut the molecule like this. I can cut the molecule like this. So now let us check the hydrogen. So I have CH3, I have a CH2, I have an hydrogen here, hydrogen here. So always try to write the hydrogen so that you don't miss anything. So I have hydrogen 1, 2, 3. So these two are same, these two are same, and these are also same. So I have three hydrogen signal here also. Okay. So but they have asked for two signals in proton NMR. So I've also found the number of carbon signals, number of proton signals, and I find that option A is the right answer. Particular problem comes from June 2012, which talks about number of signals in broadband decoupled C13 NMR. As I told, I have not gone into details of spin splitting, but just to make a clarity over here. So broadband decouple means the coupling between carbon and hydrogens are completely lost. So every single carbon will come as a singlet. So every single carbon will come as a singlet without any coupling with the neighboring hydrogens, okay, or attached hydrogen or neighboring, and no coupling, no coupling at all. So each carbon, each different carbon will give you one signal. So I have different carbon, I'll get different signals. So I have 10 different carbons means I'll get 10 different signals. So that is what talks about a broadband decoupled C13 NMR. Each carbon will give you a singlet. Each different carbon will give you a singlet. Okay. Now let us check this particular problem. They asked for spectrum of phenanthrene and anthracene. So I've given the molecular structure for them. Now cut the molecules. Very simple. I'll cut the molecule like this here. For this molecule, cut like this, and I can cut the molecule like this. Okay. Okay. So now this molecule will cut only into half, but here I can cut into four pieces. So any one of the quadrant, if you check, that will be the answer. 1, 2, 3, 4. So 4. Anthracene, 4 carbon signals. And phenanthrene 1, 2, 3, 4, 5, 6, 7. So phenanthrene 7, anthracene 4. Answer is option C. June 2011 question, again broadband decoupled carbon NMR spectrum. The number of signals for bicyclooctane. So bicyclic system, they're given A to C. See, now you people do it yourself. Okay, you pause the video and do it yourself. Okay, I hope you have done it by yourself. Okay, let's do it and see. So I can cut the molecule like this. I can cut the molecule like this. Is it not? So these are the mirror planes I have. So I'll just cut the molecule like this. So any one of the quadrant, if you check, you'll get the answer. So 1, 2, 3. So I have this molecule has three signals. Now you see in the option A and option C, I have 5 for A molecule. So option A is wrong, option C is wrong. So among B and D, I have to get the right answer. Now B, you can see that B, I can have a axis symmetry. I can just rotate them like a fan. If I rotate them, these two carbons, so these two carbons, they all are same. So I can rotate them, I can cut them into equal half, so they all are same. So what will happen? So I'll be having this carbon, this carbon, this carbon, these carbons, these all which have inked in green are same. So one signal. And the one which I've inked in red will be the second one. So they all, so I'll be having totally two signals. So 3 and 2, 3 and 2. So now the confusion is with the last one. Now let us check the last one. So last one, I can cut the molecule like this. I can cut the molecule like this in this half. So whatever lies on the other plane, so this and these are same. These and these are same. Now these two carbons are same. So this and this. So I'll be having 1, 1, 2, 2, 3, 3, 4, and 5. So since this molecule can be cut into two equal halves, it is this particular molecule is conformationally rigid. I cannot rotate the molecule. I cannot flip the molecule. This particular molecule is conformationally rigid. I cannot flip the molecule. Therefore, if I cut the molecule into two equal halves, so this is the plane of symmetry which goes like this. here. So what will happen? Whatever lies on the plane of symmetry will be chemically equivalent. So I have totally 5 signals. So answer is option B. I've just taught you a very simple method. Use either a plane of symmetry or axis of symmetry. If your protons are exchanged by this plane of symmetry or axis of symmetry, they become chemically equivalent. They are homotropic or enantiotropic. So homotropic protons and enantiotropic protons are chemically equivalent. They'll give you same signal. They'll give you same signal. Only if you have a chiral carbon, only if you have a chiral carbon, then what? The geminal methylene hydrogens and the geminal methyl groups, they'll become chemically non-equivalent and they'll give you different signals. Okay, next problem. This particular problem is asked in GATE 2019. They're asking for number of proton and NMR signals. So this molecule can be cut like this in the center, and these are bent groups, so they will be aligning with the plane of symmetry. And now you can count the number of hydrogens. So A, so this CH3 and this CH3 are same. So B. Now this hydrogen and this hydrogen are same. So C. This CH3 lies on the plane of symmetry, therefore it is D. Now you have hydrogens here. So H. So I've already mentioned, whenever you have a cyclic system, always try to write the cyclic system in the structural formula whereby you have hydrogens. So these two hydrogens which are above the plane, so I'll be having E, and these are below the plane, F. So E hydrogens are syn to the CH3 group, this CH3 group, and F hydrogens are like they are almost anti-periplanar. They're not exactly anti-periplanar, but they're almost anti-periplanar with this particular DCH3. So I have totally A, B, C, D, E, F. So I'll be having 6. So answer is the number of proton NMR signals observed for the following compound is 6. GATE 2013 problem. The number of signals that appear in proton decoupled carbon NMR of benzonitrile. They've asked for number of carbon. Okay, so I have carbon here, carbon, CH carbon, CH carbon, CH carbon, CH carbon, and CH carbon. I have a plane of symmetry cutting the molecule like this. Now, what is the answer? Carbon A, B, these two are C, these two are D, and this is E. So 1, 2, 3, 4, 5. So I have 5 signals in the carbon NMR. Okay. The nitrile carbon, then this carbon attached to the nitrile, this is different. Then the carbon which is para to the nitrile, that is different. So 3, and these two lie on the plane of symmetry, so they are same, and these two are same. So totally I'll be having 5 signals. Next problem is GATE 2009 problem. Number of signals for broadband decoupled carbon. See, again they have asked for carbon, and they asked for ortho, meta, and para dichlorobenzene. Very simple problem. So ortho dichlorobenzene, meta dichlorobenzene, and para dichlorobenzene. Para dichlorobenzene. Now cut the molecule. I can cut this molecule like this. Here I can cut the molecule like this. And this molecule, it is exactly the same substitution on the either side. Therefore, can be cut like in 2 ways. So I can cut the molecule like this in 2 ways. So I can cut this molecule in 2 ways. So like this, and then both perpendicular planes I can cut. Now count the number of carbon. So I have a carbon here. So these are CH, 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 and CH. So first let us label them. Let's label them quickly. Let us find the number of carbon signals. So this becomes carbon A, B, B, C, C. So this has 3 carbon signals. This one A, these 2 carbon, they are lying on the mirror plane. So B, so these are C, and this is D. So 4 carbon signal. Now compare this. So I have a CH, 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 CH. All the 4 are same. Therefore, I'll be naming these. All are A carbon, and the carbon attached to the chlorine, they become the B carbon. So here I have 2 signals. So whatever lies on the mirror plane, are identical. They are chemically equivalent. So 3, 4, 2, which is the option A. So option A is the right answer. Very good. Next problem, I've chosen a number of proton NMR signals for compounds P and Q. So the compound P and Q. Okay, so first write the hydrogens quickly. So they are para substituent. So I can cut the molecule like this, but I cannot cut perpendicularly. So now identify the hydrogen. So these are A, B, B, and these methyl hydrogens become C. So methyl is CH3, so C. So totally I have these one, these two put together two, and I have three signals. So this molecule gives me three signals. So when I say three, option C is gone, option D is gone. So I have option A and B, both can be, A and B are now in the shortlisted. Okay, so they have been shortlisted. Now compare the molecule Q. So I have a CH2 here, I have a CH3 here, I have a CH here, and I have two CH3. So now label them. So CH3A, B, C, these two put together D. So 3 and 4, 3 and 4 is the right answer. There is no chiral center here. Therefore, the geminal dimethyl will be chemically equal, and therefore the answer is option A. 2018 question. Among the following hydrocarbons, how many of them would give rise to three groups of proton NMR peaks with 2 is to 2 is to 3? So they're saying three different types of protons. So three different types of protons. So three different types of hydrogen, and with the intensity ratio of 2 is to 2 is to 3. Now let us write the molecule. CH3, CH2, 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 CH2. So 1, 2, 3, 4, 5, 6. So CH3. So now you can see here, these and these are same. So A, these two are B, these two are C. So A has 6 hydrogens, B has 4 hydrogens, and C has 4 hydrogens. So the ratio becomes again, it is 2 is to 2 is to 3. Now look into the second and third molecule. Let us choose this molecule. CH3, CH2, 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 CH3. So these two are same. A, B, B, C. So again I have three kinds of protons, but the A protons are 6 hydrogens, B are 4, but C are just 2. So I have 1 is to 2 is to 3. So the B is wrong answer. Let's check the last molecule. Let's check the last molecule. So I have a benzene ring. Benzene ring has 4 protons. Benzene ring has 4 protons. Then I have a CH2. I have a CH2. I have a CH3 and I have a CH3. Now this CH3 and this CH3 are same, so they'll become A protons. The CH2 and CH2 are same, they'll become B protons. And all the aromatic hydrogens, they'll be identical because I have identical substitute on either side. So I can cut the molecule like this and cut the molecule like this. So I'll be having C protons. Now number of protons, just count. A, you have 6 hydrogens. B, you have 4 hydrogens. And C, you have 4 hydrogens. So again, it comes to be 2 is to 2 is to 3. So this is 2. If I divide by 2, each one of them, it will be 2 is to 2 is to 3. So what we have found, first molecule is right, second molecule is wrong, third molecule is right. So how, among the following hydrocarbons, how many of them means it is answer is 2. JAM 2020, the compounds which will have only 2 signals in proton NMR in the ratio of 3 is to 2. Don't think that they're confusing it. There's nothing to confuse. Very simple problems. Just try to do them. So let us do the first molecule. You have a plane of symmetry here. So cut the molecule into two equal halves. So you have CH3, CH3. You have hydrogen, 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 hydrogen. So they're asking for only 2 signals in proton NMR. Here I have A, B, C. I have 3 signals in hydrogen NMR. 3 signals in proton NMR. Therefore, A is obviously wrong. Now get to see the second molecule. I have a CH3. I have an hydrogen here. I have an hydrogen here. I have an hydrogen here. I have a plane of symmetry in between. So I have A proton, B. These two are same, C and D. So I have 4 hydrogen signal. So B is also wrong. Now come to the C molecule. Cut the molecule like this. You can also cut the molecule like this. All the 4 aromatic hydrogens will be equivalent because I've cut the molecule into 2 equal halves. So I'll be having total number of signals. So this CH3 and this CH3 will give me A signal, and all the aromatic hydrogens together will give me B signal. Okay, so the ratio, I have 6 protons corresponding to A signal and I have 4 protons corresponding to B signal. So when I divide them by 2, I get 3 is to 2. So this molecule seems to be correct. Now look into the last molecule. I have CH3, C double bond O, CH2, CH2, C double bond O, CH3. This molecule can be cut into 2 equal half like this. Is it not? Now check here. So these are A, B, B. They lie on the plane of symmetry. So now I have A 6 protons and B I have 4 protons. So the 6 protons corresponds to A signal and 4 protons correspond to the B signals. Now divide by 2, I have 3 is to 2. So what we find, the option D is also right. So here the answer is C and D. Multi-select question. So multi-select means more than one answer will be right. So here option C and D both are right. So JAM 2020, a recent question. So this particular molecule is a biphenyl. You can cut the molecule in 2 equal half like this. You can cut like this. So they can be rotated, all that stuff. So only, so if you count the number of hydrogen in any half of the benzene ring, that will be the answer. So CH3, hydrogen and this CH3. So let us check. So I have A, B, C. So just 3. Because here this A, this will be also A, this will be also B, and you have a C here. And so the same thing will correspond to this side of the molecule. So the answer is 3. Okay, the last problem for this video is JAM 2023. They've asked for number of signals observed in proton NMR. So it is singlets actually. So we have to look into the coupling parameters. So spin coupling, but here we can stick on to the number of signals, so they will remain the same. I'll discuss about this in the next video regarding the spin coupling and spin splitting, whereby I'll detail you regarding the coupling between the neighboring partners. So here, so I have this CH3, this CH3, this hydrogen, and you have a methyl. Okay, so I can cut the molecule. Yes, I can cut the molecule like this into 2 equal half. So when I cut the molecule into 2 equal half, what happens? This both become A proton, this both become B proton, methoxy proton become the C proton. So I have totally 3 different types of hydrogen. So the answer is 3. So the next video will talk about the spin coupling and spin splitting. So I'll be talking about spin splitting and spin coupling. I'll be talking about the coupling constant, and I'll be talking about the types of coupling and more. For the learning check, I've attached a Google form link in the description. Try to solve the problems. Stay tuned for more videos. Thank you.